Okay, so today we are starting with interior and exterior angles, and I'm going to start with I know this scenario is not in your note packet, but I still want to read it to you to kind of show you when would I ever need this, Miss Benton? Why do I even care about angles inside of circles? So here's a scenario. You're flying a plane, or maybe you're the air traffic controller, and you're looking at your radar here. So here is your radar, and here is one plane's path, and here's the other plane's projected path. Okay, and it says two airplanes narrowly miss hitting each other by a few feet. Below is their paths on the radar, assuming that the two planes stayed at the same altitude and arrived at the same point at the same time. How many degrees should flight 3456 have turned in order to not hit flight 7890? Okay, so here's the scenario. Let's pretend this is flight 3456, and they're flying at the same altitude, and then here comes flight 7890 coming this direction. So if they're at the same altitude and they're arriving at this point of intersection at the same time, the best way for them to not intersect is for this plane to turn her nose this direction so that she's flying parallel to this other plane, and then they would not intersect. In pretty much any other scenario, they're going to intersect if they're arriving at the same time at the same altitude. So the question is, what are the degrees of this angle? And so if you knew that each one of these is 15 degrees, which it is, we could figure this very problem out with what we're going to learn today. How many degrees does our plane need to change the nose, the direction of the plane? So before we can get into all the how to solve that scenario, how to prevent disaster, you need to know a few words, a few vocab words. So three kinds of lines we're going to talk about that cross circles. The first one is going to be called the tangent line. We've seen that word before, tangent, when we dealt with SOHCAHTOA, right? Tangent being opposite over adjacent is related to the tangent we're talking about here. It's not the exact same idea, but the TOA, tangent is opposite over adjacent, gets its name from this kind of tangent, which is a line that intersects the circle in exactly one point. So that's this line right here, and it touches the circle right here, and that's the only place it touches the circle, at that one point. Okay, then you have a chord. A chord is a segment whose endpoints are on the circle, and we've talked about a chord are on the circle. We talked about that the diameter is a type of chord, right? It goes all the way through the circle, endpoints on both ends. And then notice that a chord is part of a bigger line called a secant. And a secant, so maybe not the whole secant is shown every time. Maybe sometimes just the chord is showing, but just know that if you were to extend a chord out, it would be called a secant, and it intersects a circle at 2 points. So it's like Cupid's arrow. It goes all the way through the circle and comes out the other side. So tangent only touches the circle at one point, secant goes all the way through the circle, and chord is just the part of the secant that's inside the circle. Okay, so now that we know that, we can go to our first theorem of the day. And so it says this is for interior angles, because what we're looking for is angle 1, and angle 1 is somewhere inside the circle. Okay, so if you go back to your strategy sheet, so I'm talking about that purple sheet that we used last class to look at a couple of different strategies for looking at angles inside of circles, that purple sheet. So let's just review real quick, just to bring everything all back full to the same place. So the central angle is when the vertex is on the center of the circle. An inscribed angle is when the vertex is on the rim of the circle. Now we're moving on today to strategy number 3. We're talking about an interior angle is when your angle is somewhere in the interior. It's not on the rim, but it's also not on the center. So it's just randomly somewhere in the interior. That's what we're talking about in our new strategy, is when that happens. So let's go back to our notes. So this new strategy says the measure of an angle formed by two lines that intersect inside a circle. By the way, what kind of lines are these? We just learned that new verb, the new vocab word is what I'm trying to say, is those would be what? Secants, because they go all the way through the circle. So some geometry books name this theorem based off of the fact that this is two secant lines intersecting inside a circle, or technically it can even be two chords. You don't even have to have the full secant. Intersect inside a circle is half the sum of the measures of the intercepted arcs. What the snot does that mean? It means if I want to find angle 1, I get the arc in between where those two lines cross on that side of the circle, and I get the arc over here on this side of the rim of the circle in between those two intersecting lines. And then I take x and I take y, I take the measure, the degrees of those two arcs, I add them together, and I divide by 2. In other words, find the average of the arcs. And if you think about it, that makes sense, right? Because when it was exactly on the center, it was the exact same amount as this guy. And when it was exactly on the center, it was the exact same amount as this guy. But when you're somewhere floating in the middle, it's not the exact same amount as either one. So you just take the average of the two. So we said you take the green arc and the blue arc and divide them by 2. So let's try this out in the next video.